Okay, good morning on this very magenta morning. Anyway, I hope everyone had a wonderful holiday weekend and you're ready to get back into things. Before we get started today, does anybody have any questions over maybe anything we talked about last time, anything you've thought of in the last week? Okay, then for just a couple announcements. Number one, the first homework assignment is now posted. You should be able to see it on Blackboard. We're still going to be in this unit for a little while. It's going to be all of today's lecture as well as pretty much all of next week. So the homework is not due for essentially another 2 weeks. It's due Monday. I think that's the 18th of September. So go ahead and start looking at it. We're going to be through quite a bit of the material today. Probably not enough to answer every question on the homework, but certainly that you should be able to start it and get through some of them. If you have any questions, remember if they're general questions, please post them to the discussion board on Blackboard rather than emailing me directly, or bring your questions to class. One other announcement that I have, if anyone's tried viewing the echo recordings from last week of the lectures, as I said on Wednesday, Monday the system just completely failed and there was nothing. If you went and tried to look at last Wednesday's lecture, it captured the video of me walking around like a fool up here in the front just fine, and it got the audio just fine, but it completely whiffed on the computer output. I have alerted DoIT to this problem. Last I heard from them, last Thursday or Friday, I don't remember which day it was, they had come in here and apparently there was something epically wrong with the system that they had never seen before. They were not sure what the problem was, and they're working on it. They're hoping to get it fixed as soon as possible, but until that happens, I don't know how useful the echo recordings are going to be. I just wanted to let you know that I know about the problem, they know about the problem, and hopefully it will be resolved soon. But it seems to be a problem with the actual equipment here in the room rather than anything that I did screwing up the setup of echo recordings. Okay, so I was really hoping this would fix itself. Let's see what we can do here. Because that's going to be really annoying if we've got that wonderful magenta backdrop. Come on. Figures. Okay, I tried. In the meantime, we will just have very magenta slides today. All right, so what were we discussing last time? I know, I'm asking you to think about a week ago. Okay, so we started our discussion of GPS. And we spent a little bit of time talking about some of the history and the context of GPS, why we use this, why we developed it. Just as sort of a quiz of sorts, unofficially. Who paid for GPS? The government. Can we be more specific? Okay, the U.S. government, yes. Can we be more specific? The military, the Department of Defense, pretty much footed the bill for GPS because it had a lot of wartime applications when they started developing it back in the mid-70s. Okay, and then once it was deployed in the 90s, they realized that it had lots of other applications leading to, helping people find directions using their cell phones and other things. But that's not what it was originally intended for. And so one of the key lessons that we get there is that technologies often find uses well beyond what they're originally designed for. And we're going to see that as sort of an ongoing theme as we work through the different units this semester. Once we finished up that discussion, we spent a little bit of time talking about one physics concept, and this will be one of the few physics concepts that we actually discussed this semester, of dealing with this idea of speed, distance, and time, and what's the relationship between them. We worked a couple examples. We're not going to go back through it in great detail today. And so a few of the other key points. Okay, that's going to be really annoying. I apologize that this text is so hard to read. I did not expect a magenta projector when I made these slides. I would say you can view them on Echo, but we'll find out if that's true. Either way, the slides will be posted to Blackboard after class today, and hopefully they will look better on your laptop or on your computer. One of the other things that we were able to see immediately from the speed, distance, and time example was that we need very accurate clocks for the GPS system to work. And that's simply because it only takes maybe a few hundredths, at most a tenth of a second for a radio signal from one of these GPS satellites in orbit to reach us down on the surface. So if our clock is going to be off by, even just a few hundredths of a second, that's going to make a big difference when trying to figure out what is our location. And we're going to see that point come into play a little bit later, probably close to the end of lecture today. Okay. So we talked a little bit about distance. We talked about trilateration. What was the difference between trilateration and triangulation? Does anybody remember? Anybody tell me what trilateration or triangulation are? Mm-hmm. Right. So triangulation was a way of using angles to figure out what our location or what our position was. Trilateration instead used actual distances and very much relied on geometry and how do circles and spheres and things like that help us. As sort of pictured here, where we see there's a bunch of satellites and spheres around them and the planet Earth. We're going to come back to this point, and this will be the primary focus of our lecture today. And so where we sort of closed down our lecture last time was with some very simple 1D examples where we said, okay, well, we're going to put a satellite at some particular point. And this example is maybe at the origin. We're going to know that it emits a signal. We're going to know the speed of that signal. Just like in a GPS application, the speed of our signal would be what? How fast do radio waves travel? Speed of light, essentially. Okay? So we know that. And we're going to know the time that it took for that signal to reach us. In this first example, it was simply 3 seconds. This is by no means a realistic example from the GPS perspective. And so if we know the satellite was here at point 0, at the origin, it took 3 seconds for us to receive a signal that was traveling at 4 miles per second, what could we determine about our position from this amount of information? Right, we figured out we could get it down to 2 places. This information allowed us to figure out, okay, using that speed, distance, time relationship, signal traveling at 4 miles per second that travels for 3 seconds means it had to travel 12 miles. So what we know from this measurement that we got from this satellite was that we are 12 miles away from the satellite. What was that? Right, we just don't know the specific direction. There's our pen. And so what ends up happening is, if the satellite is right there, we know we're just 12 miles away, whether that's here in the negative direction or 12 miles in the positive direction, we don't know yet. We just don't have enough information to answer that question. And so what did we do to try to solve that situation moving forward? What was that? Yep, we added another satellite. And so we came to this other second example where we said we still had that first satellite from last time, which said we have to be at either plus 12 or minus 12. But if we added another satellite, suppose it's at a different position, so this one is now positioned at -4, we can measure how long it takes to receive a signal from that satellite. And in this case, it was just 2 seconds, which told us we were maybe 8 miles away from the second satellite. And so what we ended up finding when we worked through this was if we had satellite 1 was here at 0, we knew we had to either be at 12 or -12. Our location had to be one of those 2 spots. Satellite 2 comes in now. It's positioned a little bit differently, here at -4. And we know that we have to be 8 miles away from that satellite because of the fact that it took us 2 seconds to get that signal, and the signal was traveling at, what was it, 4 miles per second, I think from the last slide? So what possible positions could we be at based on this second piece of information? We have to be either at -12 or 4, because those are the 2 points that are 8 miles away from 4. We could either be here at 4 or over here at -12. And so when we combine both of those pieces of information, so we had the measurement from the first satellite that we saw on the last slide, and now this extra measurement, can we actually determine what our location is? Yeah, it has to be -12. That's the only location that's consistent with all of the information we've acquired. And this is exactly the premise that GPS uses when figuring out our location. We have to have measurements from some number of satellites to narrow down the information to determine precisely where we are. Okay. Clear all of this off. Okay. And so then we sort of ended last time. There was one other example where things didn't work out right. And it turned out that the 2 pieces of information, the thing that we got from the first satellite and the information we got from the second satellite, didn't match up. there was no position that was consistent with everything, and this could be an internal safeguard to make sure that the system is working. In this case, if this were a diagnostic, it would indicate something's wrong, and either the Air Force needs to go make sure the satellites are working correctly, or we need to make sure our phone or our GPS receiver is working correctly. Something was wrong. We're not going to dwell too much more on that point as today goes on. And so I believe this is actually where we ended last time, was trying to step back from the problem a little bit and ask ourselves, well, now that we've seen GPS, we can ask ourselves the question, how many satellites do we need to see to determine our location? How do we determine some sort of mathematical way to approach this problem? What's sort of the common theme? What's the structure of what we've been looking at so far? And what this all boils down to, and again, I apologize that the text is so hard to read on the screen this morning, is what we really get is a system of equations. Okay? So what ends up happening, basically, every satellite signal that we're going to get is going to give us an equation that looks something like that. Where what this is really saying is we've got some speed times time, which is to say, what's speed times time? That's a distance, is equal to some distance. And so what happens is this s times t tells us that's the time we measure from the satellite. That's something we get from our GPS receiver. And then we have this d over here, which is everything under that square root sign. That's now a distance that incorporates these two variables, x, and what's labeled here is x sub 1. X is maybe our position. Is that something that's known or unknown? Was that? Well, that's what we're trying to determine. If we're trying to figure out our position, is that known or unknown? It's an unknown. That's what we're trying to solve for. And so then if x is our position and x1 is the position of the satellite, is x1 known or unknown? Known. We have to know the positions of the satellite. And so what we end up getting is for each of these measurements, so satellite 1 gives us an equation that looks like this. Satellite 2 gives us an equation that looks like this. Now, T1 and T2 are probably different. It took a different amount of time for the radio signal emitted by satellite 1 to reach us than it did for the signal emitted by satellite 2. It's always possible those times could be the same, but that would be just complete circumstance. Just as much as, what about x1 and x2? Are those going to be the same or different? They're going to be different. What would it mean if they were the same? That would mean that the satellites were on top of each other, and that's probably not really all that practical. Typically, when satellites collide, they blow up. Okay? And so what this boils down to is we've got now this system of equations. As written here, how many equations do we have? 2. And how many unknown variables do we have? 1. Just x, our position. This should be something we can solve. And when we say be able to solve the system of equations, what that means is that we're looking for a value, x, that simultaneously satisfies both of the equations. Okay? And so think back before. We saw in that last example, if we looked just at the satellite 1 equation, the one that's circled here, we learned that x could be plus 12 or minus 12. When we added then the second equation, this one down here for the second satellite, we saw it could be 4 or minus 12. Only one of those values in each case satisfied both of the equations. And so when we want to think about the solution to the entire system, that's the only possible choice. And we've gotten it down to a unique value. In the context of GPS, that then has to be our location. Okay, while I raise, does anybody have any questions about this? We'll talk about this a little bit more in the next couple slides. Okay. If not, then, so just to make this a little bit spelled out, we've pretty much already said this. You know, system of equations is just a set of equations that involve the same unknown variable or the same unknown variables. In this case, there was only one unknown variable. It was just x. And the solution provides values for all of the unknown values that simultaneously satisfy all of the equations in the system. Okay, so as we said, for our previous example, we had these two equations, and we could see that there's this same unknown, this x value, which is, again, very hard to see on the screen. and our location is any possible x that satisfies all of the equations. So let's step back and think about our example from more of this mathematical perspective when we had maybe just the one equation. So pretend that one's not there. We don't have that piece of information. How many solutions did this system of one equation have? It had 2. Okay, was that useful for our GPS application in trying to determine what is our position? No, because we knew, well, we're at one of 2 locations, and that's better than not having any clue where we are, but it doesn't tell us exactly where we are. And so then we would add another equation and try to get that information narrowed down. And when we did that, that worked just fine. Okay, so just for a little bit more, language can be a very powerful tool. I'm sure if any of you are studying linguistics or English or something like that, I don't have to convince you. And developing ideas and terminology that help us describe a system or describe anything can be very useful. When it comes to systems of equations, there are a couple different labels that we're going to want to use that are going to help develop this unit. And so one of the things that we can do, and I apologize that all of the keywords are again in red for emphasis. I will send a ticket to do it after class today and let them know the projector's having issues. The set of all solutions, when we take our system of equations and we look at all of the solutions that we could be, that's called the solution set. Okay? Does there have to be only one solution? Not necessarily. Does there have to be a solution at all? Have we seen an example where we had maybe 2 equations and there weren't any solutions? Yeah, we saw one of those. Okay. So, if a system doesn't have a solution, as we said, we've seen that's possible, we can call that system of equations inconsistent. There's just no solution. We can't find any values that satisfy everything. Conversely, if the system has a solution, what might we call it? It's consistent. Okay? And so then, as we mentioned, the solution doesn't have to be unique. Come on, go away. There we go. It doesn't have to be unique. There could be 2 solutions, 3 solutions, 4 solutions. There could be an infinite number of solutions. When we're thinking about our GPS example, do we want a unique solution? Yeah. Why do we want that unique solution? Right, because we're going to interpret that unique solution as our position. We keep gathering more and more and more and more and more information from the different satellites. Each one of those satellites tells us a little bit more, helping us narrow down what is our position. And we know we don't need to gather any more information when we've only got one possible position that's consistent with all of the information we've gathered. At that point, we have to know deductively that that position, that solution to our system of equations, is our position. Okay? And so, what we're going to be doing then, when we think about our question, how many satellites do we need to determine our position? When we think about turning this over into a mathematical problem, what we're really asking is what's the minimum number of signals, what's the minimum number of equations that's going to give us a unique solution. Okay? And what allows this problem to be particularly straightforward to answer is the fact that when we're thinking about our GPS example, every equation that we get, every signal that we get, is going to have a particular form. It's going to have this speed times transit time equals distance form. And once we know that, we can actually address this question pretty straightforwardly to determine what is that minimum number of equations, what is that minimum number of satellite signals that we need to determine our location. And that's what we're going to spend pretty much the rest of today investigating. Before we jump into that, does anyone have any questions? This is sort of the guts of the unit right here in these last couple slides. The first one that's in the red that's hard to read, solution set. Yeah, like I said, the slides we posted after class today, so I apologize, they're very hard to read on the funky projector today. Other questions? Yeah. Mm-hmm.
In X, but also in Y and Z.
Yep.
It doesn't
Okay, so you'd think I'd paid you or something. You'd think I'd paid you to ask that question. I did not, as it turns out. But the question was, well, so far, we've only been considering these 1D examples, which is sort of a nice warm-up, but not really relevant to the real world, because in reality, we live in how many dimensions? 3. So how does this generalize and how does this build up? That's exactly what we're going to be talking about for the next couple minutes. So I guess that's a good segue then to move on. Just as a note, I put this in here more just to sort of make a small point. We're not going to go into how do you actually solve systems of equations. We'll talk about a different way of doing this here momentarily. I just wanted to put up, though, in this simple 1D case where we had these two signals, you could actually algebraically manipulate these equations and come up with a solution that looks something like this. The one reason why I'm pointing this out to you is that this may not always be a great idea. One of the reasons why is that this suggests that there's always a solution. Given the speed of light, or whatever our signal speed is, given those transit times for the two satellites, that T1 and T2, given the positions of those two satellites, this equation says that's how you would determine your location, at least in this 1D world. But thinking back, we saw that one example where we had that inconsistent system of equations. There was no solution. What gives? We could plug in those values. What's wrong here? Because this is saying we should always be able to find a solution, but then we've already seen a system where there wasn't a solution. So what happened? Does anybody have an idea? Yep.
It doesn't account for problems with the satellites or with your GPS receiver.
Well, it doesn't account for the problems, but in principle, I mean, that example was a good way to check to see if there were problems, but it's a completely necessarily realistic example, where you said the satellite is here, it took this amount of time, satellite's here, it took this amount of time, and just nothing came out. That should not happen in practice, but from a mathematical perspective, there's nothing wrong with it. Yeah, physically, it makes no sense. And that's sort of the point. The issue here, as we went through this solution strategy, we actually had to square those radicals in both sides. And sometimes when you do this, if you think back to your high school algebra classes, this can introduce extraneous solutions. Okay? And so it turns out in certain cases, there isn't one. And so the key point here is just to keep in mind, and we're not going to really need this moving on in this unit at all, but I just wanted to make the point, if you're going to work with solving systems of equations, in particular when you've got sort of square roots involved, always, always, always check your solution when you're done. What do I mean when I say check your solution?
See if it works in both equations.
Right, see if it works. So we could take the value of x that maybe we obtained using this formula, plug it back into the two pieces of information, the two satellite signals that we got, and just verify that it is in fact correct. If it doesn't meet one of those equations, what does that tell us about that potential solution? It's bunk. Okay? And so as we move through this unit and as we work through this material, my expectation of you, as I said, we're not going to focus on how do we solve systems of equations. There are dedicated classes at this university that will help with that. What I want you to be able to do is to be able to verify a solution, particularly when we get to the quiz. So I might give you, here are potential solutions. Which ones are actually solutions? Okay?
Should x2 and then x21 be parentheses, or just should it be that way?
In the, right here, you're asking, should there be parentheses around this?
Yeah.
It wouldn't matter. Because you could think about just distributing that +1 and you would get the same thing. Yep. Okay, so let's erase this and move on. It will introduce, at least for some simple cases, some tools that will solve the equations for you if you're curious. But that's not going to be our main focus. Okay, so just let's take a moment for some comic relief here. The importance of checking your work. As I mentioned last week, I'm a big fan of XKCD. This is a fairly old one. Los Alamos, 1945. Anybody know what was going on in Los Alamos, 1945? Anybody know where Los Alamos is? It's not in Texas, and it is certainly still above water. It's close to Texas. Go one state west. Not Arizona, that's too far. It's in New Mexico. It's about 30 miles northwest of Santa Fe. Anybody know what's in Los Alamos? Well, it's not necessarily a nuclear testing site. It very well may have been at one point in time. We'll talk about this more in about 2 weeks. Most of those, I believe, were in Nevada, but that's classified, so I can't really attest to that with any great certainty. But more than a nuclear testing site, there is a national laboratory called the Los Alamos National Laboratory. I know, the government is very creative at naming things. Just as much as a few miles down the road, there's the Brookhaven National Laboratory, which is located in the town of Brookhaven. Okay, so what was going on at Los Alamos? It wasn't called the National Laboratory in 1945. It was called Site 2. Anybody know what was going on there in 1945? What was going on in the world in 1945? The very end of World War II. Two things happened in 1945 that have never happened since. What was that? Right, Hiroshima and Nagasaki, where the United States dropped 2 nuclear missiles, or 2 nuclear warheads on Japan, which basically ended the Pacific theater of the war. Los Alamos was one of the 2 sites in the United States that was responsible for developing these weapons in this thing called the Manhattan Project. And so, with that context, sort of the joke here, you see there's a bunch of people gathered around, presumably scientists or engineers in Los Alamos. So we have a decision. If we've done our math right, this test will unleash heaven's fire and make us as gods. But it's possible we made a mistake, and the heat will ignite the atmosphere, destroying the planet in a cleansing conflagration. Wow. Question, just to double check, although I'm 99% sure, is it SOHCAHTOA or COSATOA? Okay, the trig functions. Or for the love of, can someone redo Steve's work? I don't want to do this test anymore. Check your work. Okay. Other story on checking your work. I imagine this is probably, some of you may be a little bit too young for this. Anybody remember the Mars mission about 20 years ago? You've heard about this, where NASA sent this satellite, or not a satellite, but a probe to Mars, and it missed the planet by quite a bit of a distance. Does anyone remember why it missed the planet? Yeah, they forgot to switch between centimeters and inches. So check your work. No, I mean, this is a great lesson, though, because it shows, like, even, professional scientists and professional engineers make mistakes. Okay, that was a particularly costly mistake. Literally, I mean, that probe cost billions of dollars. And now it's just sort of slingshotting past Mars, flying off into the universe. Great. Anyway, back on. So I put on this slide just some tips if you ever encounter a system of equations, some tips that might help you in solving it. I don't want to go through it in any great detail. This is just more for your information if you encounter one of these things in whatever it is that you're doing in your day-to-day life. Because I imagine most of you are going around thinking, wow, is there a system of equations here I can solve? That sounds like fun. I know that's what you're all doing as soon as this class is over. Okay, so for some additional resources, if you're looking for other ideas, you can go to Google and just type in solving a system of equations, and I guarantee you'll find a lot of great things. A couple that might be useful, the Khan Academy has a really nice set of tools available. There's also an online tool called Wolfram Alpha. Has anybody seen or used this before? Okay, a couple hands have gone up. Well, if not, then I guess you're all going to be familiar with it in about 10 minutes here. Before we spend some time on that, just if you're interested, I mentioned there are other classes that are available that will talk about these things. Any course on linear algebra, something like AMS 210, huzzah! Damn it. So close. Something like AMS 210 will spend quite a bit of time discussing tools and techniques for solving systems of equations. So if you're really interested in this, that's a great place to go to find out more. And so what I want to do now is show you some online tools that you can use to actually work on solving these equations. Again, we're not going to focus on that, so using these online tools is a perfectly valid way to solve it, at least for the purposes of this class. Step back from the machine. Okay, let's see if we can get lucky here. So I've copied and pasted in a screenshot of this, but if we actually pull up Wolfram Alpha, so you can either just Google Wolfram Alpha, which is what I usually do because I'm too lazy to type the extra .com into the thing. But if we come up here, we can do all sorts of neat things. So we can think about saying solve x squared. I'm just putting in a system. I'm just making up one on the spot. Equals 9. And what did I have over here on the slide? X minus y equals 4. We can hit enter. There was no particular sort of heavy programming needed. There was no code involved in that. I mean, solve and are pretty straightforward words in the English language, in my mind. Maybe you'll disagree with me. But a couple things pop out. It took it a moment to process. The first thing that it does, which is sort of a really useful thing, is this box called input interpretation, where what it's doing is it's printing back out to you what it thinks you asked it to do. Okay, so if sort of you come out later and get something that looks a little bit weird as your output from Wolfram Alpha, this is a good place to start doing some checking. Just make sure it actually did what you wanted it to. And so it comes out here and says the operation it's going to do, it's going to solve, and it lists our two equations exactly as we put it in. Okay, so thinking back into some of our terminology here, so this is now a system of equations. How many equations do we have? 2. How many unknown variables do we have? 2. And what are they? X and Y. Yes. So what Wolfram Alpha then proceeds to show is a handful of results. So how many solutions do you think, based on this output, does this system have? How many results do you see? 2. We see 1. Let's see if there we go. So we've got 1 right there. Notice that it's providing a value for X and a value for Y. Okay, because we need to have values for all of the unknown values, all of the unknown variables, to be a solution. And there's also 1 right underneath it. Okay? Wolfram Alpha then also will try to visualize it for you. And so it's going to plot now those 2 equations. So we see we've got one of those equations here in the blue line. And if you were to just look at x squared plus 3y equals 9, again, going back to sort of high school algebra, what shape would you expect that to take? It's a parabola. And notice, well, now maybe it's harder to notice, but we can see that we've got sort of this blue line shaped out, and I'm bad at tracing, that parabola in that way. Okay? Likewise, we had this other one, this x minus y equals 4. What shape would you expect that to be? That's just a line. And so we can also notice here, Wolfram Alpha plotted out that line that, again, I'm bad at tracing. And at how many locations does that parabola intersect the line? At 2. Those are our 2 solutions. Okay? So Wolfram Alpha had a lot of sort of nice stuff behind the scenes to go in and figure out what are those solutions analytically, is, like saying x is equal to 1/2 times the square root of 93 minus 3. And at the same time, y would then be 1/2 times the square root of 93 minus 11. Huzzah. I know it was obvious to all of you that those were the solutions. Or that was at least one of them. Okay? So it's a really nice tool that can do lots of things. And we'll continue working with Wolfram Alpha here as we work through some of the examples to see what's going on. But as you're working on your homework, feel free to use this tool. It's quite nice. Again, it's pretty straightforward and easy to use. There's decent help pages available. If you're stumped, just Google what you're trying to do, and you can probably find some help pretty easily. And it provides some really nice output. And so if we come back over to the slides real quick, I took a screenshot of the output we just saw and included it here just for reference if you want to go home and try to duplicate this later, just to make sure everything's running right. And then what I just want to put here is just a note on using Wolfram Alpha in your homework. I think it's perfectly fine, as I mentioned a moment ago, for you to use it in your homework. What I do ask you to do, though, is take a screenshot, like what I had on the previous slide here, that shows your input. What is it that you asked it to do? And then the pertinent part of the output, whether it's the graph, whether it's this, whatever the question is asking. It's perfectly okay to use Wolfram Alpha, but please just include a screenshot to basically justify and say, well, this is me showing my work. Okay? Does that make sense? The one caveat to remember, though, is when it comes quiz time, you will not have access to Wolfram Alpha. And as I said, I'm not going to ask you to solve a system of equations. I might ask you to verify a solution where you can just substitute the values back in and make sure everything checks out. But just bear that in mind as you're working through. You won't have access to Wolfram Alpha on the quizzes and whatnot. Okay? So, as we've already seen from this example over here, we can take that system of equations and we can represent it graphically to sort of see what's going on. We had a really just quick 2D example that we made up more or less on the fly. Can we bring this back and apply it to our satellite situation? And the answer is yeah. So in 1D, it's a little bit weird. The command we're actually going to use is called number line. And what we're going to do, if you think back to that example that we started with in the beginning, we knew that our distance from that first satellite was 12, because this is where we had the signal was traveling at 4 miles per second, and it took us 3 seconds to get it. And who remembers, where was that satellite? It was at the origin. And so from our 1D distance formula, that's equal to absolute value of x minus 0. 0 is, again, our origin. We can plug that in here. And so Wolfram alpha comes back and says, well, this is a number line operation. What values of x satisfy this equation? And notice it comes out here, and there's this nice little number line plot and shows, here's a black dot saying, well, this is one possible place we could be located. And you'll notice it's down here at minus 12. And we've also got our other one up here at plus 12, which is sort of exactly what we'd seen in what I feebly tried to sketch a few slides ago. OK, well, that's sort of nice. And again, we can see this confirms what we'd already seen, that this is inconclusive. There are 2 solutions that it's reporting. We can't determine our location exactly from that. Now, Wolfram alpha is nice because it's very straightforward to add another equation where suppose we had that second satellite. We knew we were 8 miles from it, and that satellite was at minus 4. So we can again plug in the same thing now, where we have sort of that 8 right up there as being our distance, and then that formula x minus the location of the satellite, which was at minus 4. And when we plug all that in and hit enter, takes it a moment. Again, check our input, and it processed that correctly. And when we come down and we can look at the number line, what we now see in blue, we've got this absolute value, x equals 12. So that's our first satellite. And we see that there are solutions right here and right there. And then we've also got in this magenta line the information from that second satellite, which now shows we've got right there potentially as a solution and also right there. And so naturally, when we combine these two together, it becomes very clear in a graphical sense which one is the solution to the entire system. It's minus 12. And therefore, we know our position. Okay. Let me just come over here briefly. We're not going to actually run this through in Wolfram alpha. But if you were curious, where we had that inconsistent system a little while ago, what we can actually see now is when we plot this graphically, satellite 1 says we're at minus 12 or 12, which we've established that nicely. The other satellite now has these 2, and notice that there's no x point where 2 of those points line up. Okay? Which is, again, it's inconsistent. There's not a solution. We can't simultaneously satisfy all of the information, all of those equations, all of those satellite signals that we have. And so there's just no solution. All right. Any questions on all of that before we move on to something else? And by something else, what do you think we're going to do next? Coming back to your question about the idea of dimensions. Okay, you're saying coordinate system. Hold that thought. We'll come back to that next time. Okay, let's actually go now to 2 dimensions. So we've spent quite a bit of time now on 1 dimensions, looking at how do we solve it, how do we plot it, how do we work with this information, how do we understand this information. What changes when we want to think about going to 2 dimensions? Okay, the equation is changing. Well, that's one thing we're definitely going to have. Our distance formula is not going to be nearly as straightforward as just an absolute value. Instead, if you go back a few slides ago from last time, there's a square root involved, and there's a bunch. Actually, let me just write it up here. So what we're going to get now is our speed times maybe t1 is now going to be equal to x minus x1 squared plus y minus y1 squared. So now, what's the information that every satellite measurement is going to be giving us? Do we still have a transit time? Yeah, we've still got that t1 in there. But now when we want to think about the location of our satellite, how many pieces of information does that require? requires 2. We need to know both the x and the y position of the satellite. And so we have this x1 as well as this y1 telling us where is the satellite. At the same time, how many unknown variables do we now have? 2. We have x and y, because if we're truly in a two-dimensional situation, we need to know both x and y to determine our exact location. Okay? And so what's going to happen is we can sort of generalize a lot of the analysis we've already seen to now look at this case. First of all, does anybody know what type of shape this equation gives us? It gives us a circle. To see that, you can think about squaring both sides, where now you would get s squared t1 squared, and you basically just remove this root, and we end up getting the equation of a circle. And so when we think about this trilateration, if anyone went and looked at that Wikipedia page, it talks a lot about circles and spheres. This is why. Okay? So what this is now telling us is that every piece of information that we get from a satellite, every satellite measurement, is going to somehow tell us we have to be on some circle, that we're some distance away from that point, at least in this two-dimensional example. And so let's look at a more concrete example. Okay, so we've got this set here, or this example. A satellite is positioned at 2,3 and emits a signal that you receive 3 seconds later. Signal travels at 1 mile per second. What is your location? Who thinks there's enough information here to actually determine uniquely your location? Does anyone think this gives you enough? Nope, it doesn't. But what can we narrow down our location using this information? Yeah. Okay, so the couple things that we have, what was the transit time for this particular measurement? It's 3 seconds. Oop. Go back to pen. There we go. So t1 was equal to 3 seconds. The speed was equal to 1 mile per second. So our distance from that first satellite is equal to 3 miles. Okay, the satellite's location, or the satellite's position, is at 2,3. So from that equation we had a moment ago, we know that x1 is equal to 2 miles, and y1 is equal to 3 miles. Okay? And so we can now plug all of these in. We get that one distance equation. If you'll bear with me, I'll erase all of this momentarily, and then I'll write it, and then we can plug it into Wolfram Alpha and see what happens. But what we get is we get that speed times time. That was that 3 miles, that distance. And that's going to be equal to square root of x, our unknown x coordinate position, minus 2 from the satellite, squared, plus y minus 3, bringing in that satellite's y coordinate, squared. And so we know that whatever our position is, it has to satisfy this equation. So we're looking for specifically now values of x and y that together satisfy this equation. Okay, we said a moment ago that that's going to be a circle. And so let's flip over to Wolfram Alpha and see that. So what we can do, just from experience, Wolfram Alpha typically works better if you go ahead and square both sides and get rid of that radical. So we're going to go ahead and do that. And so we're going to get 9 equals, what was it, x minus 2 squared plus y minus 3 squared. Again, with that plot keyword. And so sure enough, when that comes out, we get a circle. What's the center of that circle? 2, 3. It's the satellite's location. And what's its radius? It's 3 miles, which makes sense because what we know from that information is we have to be 3 miles away from the satellite. And so that circle is telling us all of the points that are 3 miles from it. Notice, as we expected, does that narrow down for us a unique location? No. All we know is that we have to be somewhere on that circle. We have no idea necessarily where. So how many possible locations do we now have for us? There's an infinite number. Granted, it's a smaller infinity than being, anywhere in the two-dimensional plane, but it's not really all that useful for determining our exact location. So what can we do? That one satellite signal was insufficient. What do you think we do then to try to narrow down our location? We can add another satellite. Exactly. And so that's what we'll do over here. And so as we saw, when we had just the one satellite, we don't know what's going on. Or rather, we do know what's going on, but we just know we're somewhere on the circle. So we can add a satellite. And at this point, I'm not going to spell out all of the examples in texting. I'm just going to give you a table. It's a lot easier to work with. But now what we can see is, let's say we've got these two satellites. There are their positions. There's the transit time, and we'll assume that the signal is still 1 mile per second, or the signal speed is still 1 mile per second. Is this now enough information to determine our location? Okay, I'm hearing a bunch of no. Does anybody want to say yes? Does anybody also want to chime in and say no? Does anyone care? Okay, you're all laughing. I'll take that as a no. Okay, so what we can do now is we can take all of this information and we need to figure out, okay, well, what's our distance from each satellite? And to do that, we now need to look and say, well, what is our transit time and that transit speed? So our distance, 1, is equal to, well, 3 seconds times 1 mile per second is 3 miles. And this is basically the same equation that we had before because it's the same information. We now have our square root. X minus 2 squared plus y minus 3 squared. Again, bringing that position down into that distance formula. That's what we had before. Our new piece of information for satellite 2. What's that distance from satellite 2 now? It's 4 miles because it took us 4 seconds at that 1 mile per second. And so when we look at our distance formula, we're now going to have some x, our position, minus, and what value do we need to subtract off? We need to subtract off the -1 because that's that x position of our satellite. Yeah, the minus is just a plus. And then likewise for the y, what value do we have to subtract off? Another -1. And so we now have these two equations to describe it. So thinking back to our system of equations, how many equations do we now have? 2. How many unknown variables do we have? We still have 2. Do you think this system is going to be consistent or inconsistent? It's probably going to be consistent. I told you we weren't really going to spend a whole lot more time talking about inconsistent systems. So let's go. But how can we verify that the system is consistent?
Can we just, well, since we did the first thing, we pretty much put it in Wolfram Alpha the same way, so we do the same way, so it'll be 16 equals x plus 1 squared plus x plus 1.
Yep. We can put it into Wolfram Alpha and see what pops out. Okay? So we can come back over here, and we're just going to add a comma. So we're going to keep that same equation. That's the same one we had as before. Again, squaring tends to make it work a little bit better, so we'll square that 4 into 16. We get x plus 1 squared plus y plus 1 squared. And when we do that, it comes out, and we get this nice little plot. And so here in blue is the information that we had last time from that first satellite. And now in magenta, we have the information from the second satellite. Notice, each one of the satellites independently tells us we have to be somewhere on a circle. But now when we combine those two pieces of information, at how many locations do both of those circles intersect? Exactly at 2 points. So, given this information, given that second satellite, have we figured out our actual location yet? No, but have we narrowed it down even more? Yeah, we now know we're at one of 2 points. We're either here or there, because those are the only 2 points that satisfy both of the pieces of information that we got from the satellites simultaneously. Well, what are those points? Well, let's just clear this off, so we're going to do it a little bit differently here. What we need to do in that case is come up and change this plot keyword, what do you think we're going to put here instead? We're going to put in solve. And so it comes back, and we can see that our position now, one of those points is -1, 3. So we can come over, there's -1, and we can see that one plotted right there. And there's another one at, I know this was obvious to all of you when we put in these in, that one of them also is 71/25 and 3/25. Yeah, it was equally obvious to me right there. Okay, but we can use Wolfram Alpha in this way to get that, to see, sort of to visualize what's it going on, but then we could also change and put in that solve keyword and actually get numerically what are those intersections as well. Okay, so one satellite narrowed it down to an infinite number of positions, but somewhere on a circle. Two satellites in this 2D example narrowed it down to 2 points. What do you think we need to do to get a unique location? We need a third satellite. Okay. So we'll erase all of this and then advance on in the slides. And so sure enough, there's what we've already seen. And so we can add a third satellite. Just as a note, satellites 1 and 2 here are the same as the previous example, so I'm not going to rewrite those equations. But now we have a third satellite. And so what are we going to need to do? Right, we need to figure out what is that's that third equation. So for our third satellite, transit time is 5 seconds. How far are we then from that third satellite? We're 5 miles. So we've got our distance is equal to 5. And bringing in our distance equation, we'll have again our x. What value do we have to subtract off? -5, because that's our position up here. Plus a y minus 6 squared. And so we can add that in as now a third equation. Okay, so if we come over to our Wolfram Alpha, we can just put another comma. Squaring the 5 gives us 25. What do we have? We have x plus 5 squared plus y minus 6 squared. I think that was it, right? Yep. Okay. And so we plug that in. Takes it a moment. It comes out. Again, check your input to make sure it interpreted everything correctly, and notice it'll typeset it a little bit fancier for you than what we had. Comes down, and now, how many results does it tell us? 1. And that's -1, 3. So from that information alone, do we now know our location? Yeah, we're at -1, 3, because that's the only place, that's the only set of xy coordinates that's consistent with all of the pieces of information we gathered from the various satellites. And if we come down and look at it graphically, what again we see, the blue circle is that same information that we got from the first satellite. The magenta circle is the same piece of information from the second satellite. Right, and now this orange or yellow one, depending on how good your screen is that piece of information that we got from the third satellite. And notice that all 3 of them only go simultaneously through 1 point, which is our solution to that system of equations, which then in the context of GPS has to be our location. Okay? Does that make sense to everyone? Okay. Let's come back over here. We'll erase all this stuff off. And we will continue on. And so we can get that. So to sort of summarize what we've done so far, think about now the number of signals that we've got and how much did that tell us? What did that narrow our location down to? When we only had 1 signal, in 1D, that told us we had to be at one of 2 points. And in 2D, it said we had to be on a circle. Okay? When we added a second satellite, in 1D, that was enough to get our location. We now know here's where we are. In 2D, though, that then got us down to the 2 points, because we could intersect those 2 circles, and there's the 2 points where they cross each other. And then in 2D, we needed that third signal to actually determine our location. So now we can start to think ahead and think about how many dimensions? 3. Thank you for not jumping ahead to 4. I appreciate that. Okay, so if we now had 1 satellite in 3 dimensions, so this is where we live. There's x, y, and z. What do we know about our location if we have exactly one satellite signal? What can we narrow it down to? We can narrow it down to a sphere. Why? Because what that satellite is doing is saying we are some distance, maybe 11,000 miles away from that satellite. If we were to now look at all of the points in space that are 11,000 miles from that satellite, that would be a sphere with radius 11,000 miles. Okay, so if we have exactly one signal in three-dimensional space, we know we have to be somewhere on a sphere. Does that give us a unique point? No. So is that enough to determine our location? No. What do? We're going to add another satellite. Okay, so now when we have two satellites, the first satellite's going to give us a sphere, the second satellite's going to give us a sphere. What do you think is going to be the intersection of those two spheres? What shape? It's going to be a circle. I know this can be a little bit tricky to see. I scoured the internet and tried to find a graphic. I don't think this one is perfect, but it's the best one I was able to find. But we can now see, here's sort of sphere 1 in yellow, sphere 2 also in yellow, and where the two of them intersect forms this circle that's sort of shaded. The interior of the circle is shaded with this greenish color, but then it has sort of this black outline around it, sort of coming around in there. And so with those two satellites, what we now get is that we have to be somewhere on the circle. And again, asking ourselves, did that lead to a unique solution? No. So is that enough information for us to determine our location? No, it isn't. Okay, so what do? We add another satellite. What's going to happen when we add a third sphere? What's it going to reduce our information to? It's going to be 2 points. And so again, this shows up in better contrast on a computer screen than a projector, even if the projector is functioning perfectly. So take a look at this at home later. But there's sort of 3 spheres here. There's one in magenta down on the bottom. There's one in red sort of in the top right, and then the green one on the left. And you see that all 3 of them collide at these 2 yellow points. One right there, and one right there. Okay, so again, does this get us a unique solution? No. So is it enough to determine our location? Nope. So, naturally, I'm sounding like a broken record at this point. What do? We add one more satellite. And what do you think is going to happen when we add that 4th satellite? We're going to get our location. Okay, and so you can see now, we've got our 4 satellites pictured. There's Earth. This is actually taken from a GPS tutorial, not one that I gave you in the website links, but feel free to take a look at it if you'd like. But when we think about this now, so we ask our question, how many satellites do we need to see? And what do you think the answer is? 4. Or is it? Okay. So let's have a little bit of a counting game here. Take a look at that picture. We've got those 4 satellites. How many spheres do you see? There's 5. What's the 5th sphere? The Earth. Okay. So what we actually saw in the last slide was in 3 dimension. Was it 4 signals that we needed, or was it just 4 spheres? It's just 4 spheres, because we can take 1 sphere, 2 spheres gives us a circle, 3 spheres gives us 2 points, 4 spheres gives us the unique solution. Can we take for granted, at least in the GPS application, that we're probably going to be on the surface of the Earth? Yep. I mean, is the Earth a perfect sphere? No, it's an oblate spheroid, but for more information, take Calc 3. I'll see you in a later semester. Okay, but for our purposes, we will assume the Earth is a perfect sphere. Does everybody know about what the radius is? It's about 4,000 miles. It's a hair under. That's like 39. I think for the oblate sphere, it's like 3950 in 2 directions and 3975 in the other one. We'll say it's a sphere of 4,000 miles. But could we use that information to count as one of our 4 spheres? The fact that we're on the surface of the Earth. Yeah. So in that case, if we needed 4 spheres in 3-dimensional space, and we know that one of them is the surface of the Earth, how many satellites do we actually need? 3. So why do they draw the picture with 4? Are they just being superfluous? That would be convenient. Are engineers known for being overly superfluous? No, remember our discussion last time, that's why we don't have Rube Goldberg devices. Okay, so what's going on here? So the issue here comes back down to the fact that for GPS to work, we need very, very, very accurate clocks. Okay? And so, everything that we've done so far, all of the examples we've discussed, we've assumed that all of the clocks and all of that timing information that we got was perfect. Is that going to be true in the real world? Probably not. Are the clocks that we use regularly accurate to a second? Close enough, maybe. Are they accurate to a minute? Yeah, usually. Is that good enough for the GPS application? Is it good enough to know our transit time plus or minus 1 minute? No. Trivia fact about how far does light travel in about a minute? And don't say 1 light minute. It's enough to basically go around the Earth 6 times. Okay, so is that good enough if we know our time within a minute? No, because that basically means you could be anywhere on the Earth 6 times over. Okay, that's bad. And so one of the things that we need to deal with is accounting for these timing issues. How do we deal with the fact that there can be errors in all of this time? Okay, so the first question, where do those errors come in? Where can the clocks be inaccurate? Can they be inaccurate on your receiver? Does your phone have a perfect clock? No. So that's one potential source of errors, that when you pull out your phone, when you pull out your GPS receiver, it's slightly off, and it measures the wrong time. That's one possibility. Could there also be errors in the satellites themselves when they're sending out the signals? Could they be off? Yeah, conceivably. Now, which of these two problems do you think is easier to fix? The satellites being wrong or the receiver being wrong? Okay, who thinks satellite? Couple hands. Who thinks receiver? Okay, so your hand. Why do you think the satellites are easier to fix?
Because people are trained to do it, while receivers, you try to do it yourself, and then you realize you don't know what you're doing, so you call customer support. And then since it just takes a lot of time, well, there's people trained to fix the satellites. I assume that they don't break down that often.
Okay, so the argument here, I'm just repeating so the mic can hear it and it'll be on the recording, is that the satellites are maintained by extremely professional people whose job it is to make sure that these things are working. Versus the receivers are owned by stupid people like us that don't know how to fix anything, and when anything breaks, we run to the Genius Bar. Oh, wait, I don't have an iPhone. I don't run to the Genius Bar. And we have to get someone to fix it and go to customer support and customer service and deal with those wonderful people. That's accurate summary? Okay. So someone who said they think the receivers are easier to maintain, why do you think that? Yeah. Okay, because it's easier to fix something on Earth than in space. Those are both two very good arguments. Okay, so what ends up happening? Oh, there's a question first. Oh, yeah. Yeah. Right. Okay, so the idea here is maybe we can use atomic clocks. What's an atomic clock? Has anybody heard of atomic clocks? Okay. So first of all, there's a link here. If you click, I think, on Wikipedia page, it'll take you to that if you want to get a little more information. What is an atomic clock? Yeah. Okay, so it's an extremely accurate clock that's accurate to fractions of a fraction of a second. That's accurate. That's accurate. The way that this works is it uses oscillations in the atoms that's very much dependent and built on quantum mechanics, in certain cases even relativity, but extremely accurate. These atoms are very, very, very regular. And so we can use these atomic clocks to get very accurate timing information. And so maybe we could use these to the point that now the error involved in the clock is actually less than what's going to be engineeringly meaningful. So if we can get the error down on these clocks to maybe, I don't know, a couple microseconds or even tenths of a microsecond, is that sort of error going to really impact our GPS analysis? where we need things to be accurate about on the order of milliseconds to maybe a tenth of a millisecond. Is it going to matter for a couple tenths of a microsecond off? Probably not. Okay, what's the problem with using atomic clocks? They're expensive. If you want to take a ballpark guess, what does a good atomic clock cost? $300? Okay, that's a good guess. Anybody else want to have a different guess? $500. I see we've got some big spenders. Oh, wait, I'm sorry, you're college students. Anybody other guesses? Yep. At least 6 digits. You're getting now more in the ballpark. 7 million would be a really good atomic clock, I hope. Or the one sold by Steve Jobs. I have an Apple computer. I'm allowed to make fun of Apple. Okay, so what it turns out is a good atomic clock is usually on the order of $50,000 to $100,000. Okay, so now atomic clocks are great because they give us the accuracy we need, but they're that expensive. Are you willing to pay $50,000 to $100,000 for your cell phone? No. I'm not either. Are most people willing to pay that amount of money for their cell phone? No. So putting an atomic clock in your receiver now seems impractical. Not because we can't do it. We could, engineering-wise, it's not that hard to put an atomic clock. They're not necessarily that big. It's just an issue of cost. However, does anybody remember what was the amount of money it took to build the GPS system? It's about 12, was it 12 million or 12 billion? I think it's billion. $12 billion, and that was in like $1970. Okay, so account for 47 years of inflation. What does it matter? So we have, what was it, 24 satellites? It's 12 billion. There's about 24 satellites. Let's even round that up, but let's say there's 50. We've got a completely redundant backup set. There's 50 satellites. How much is it going to cost to put an atomic clock on each of those satellites? $5 million at the upper end? What's $5 million in a total budget of 12 billion? Nothing. So did it really cost anything at all to necessarily put these atomic clocks on the satellites? Nope. No one's even going to notice. That's a rounding error when it comes to the Department of Defense. Okay? So this is why it's actually easier to account for the problems in the satellites. Number one, there's a lot fewer of them. And number two, compared to the budget that it took to get them all up and operating anyway, this really wasn't that expensive. Okay? And so the errors that end up coming in, satellites are extremely accurate. They have fantastic clocks in them. And so what we're going to do is assume for the rest of this unit that these satellites are correct. When the satellite says it sent the signal at this time, it meant it. Can we assume our receiver is that accurate? No, we can't. And so what we can end up doing is using a little bit of mathematical trickery, nothing complicated, to deal with this problem. Okay? And so the way that this works is we can think about now what it is that we're actually measuring versus what it is that we actually want to use. So what I've got shown up here at the top is our distance equation in 3 dimensions. So notice for each of these satellite measurements, we've still got our time. It's a little bit to the left of the arrow where that TI is. And we know the position of the satellite, that xi, yi, and zi. So each of these satellite equations is going to get, or satellite measurements is going to give us an equation of this form. How many unknown variables do we have in this equation? 3. We've got our x location, our y location, and our z location. Okay. So now let's spend a little bit of time thinking about time. I know there's a police reference to synchronicity on the last slide. Insert like the sticks too much time on my hands reference here. Yes, I like 80s rock. Okay. But now, when we put this little t sub I here, what is it that we actually want there? What are we intending that to be? Is that the time as subject to errors and clock offsets, or is that the actual time it took the signal to get from the satellite to us? What do you think? When we talk about that transit time, is it, do we want that to be the transit time with some error, or do we want that to actually be the amount of time it took the signal to reach us? We want it to be the actual time because we want the actual distance. Okay? And so the way that we can think about this now is that this is the arrival time, when did our receiver get the signal, as measured by the satellite's clock, right? Because we're going to assume the satellites with these really highfalutin atomic clocks are accurate, okay? And relative to that is now the departure time. When did the satellite send the signal? So in this sense, this is now the actual time. This is the amount of time it took the signal to reach us. The problem is that the quantity that we can measure? Does it put in there the arrival time by our receiver's clock? Do we see that listed anywhere on there? No. Okay. So what we can do is have sort of this other fictitious time, which I'll denote by sort of capital T, which is now the arrival time by our receiver's clock. Is that something that we can actually measure? Yeah, because we just turn on our phone, we look for the signal, and we note the time that we find it. And we're going to subtract that off the departure time by the satellite's clock. How might our phone, how might our receiver know that value? Anybody have an idea? What was that? How would you calculate it? It's known. The Department of Defense will say the satellites will send their signals at regular time frames at, I don't know, every second, every 2 seconds. I don't know exactly what the engineering specs are. But the Department of Defense and the GPS system says, we will make known to you when the signals are sent. Maybe it's buried in the signal and there's some sort of error detecting code. If you don't know what an error detecting code is, stay tuned for about 4 weeks. We'll come back to that. But we can code things in that signal. And so maybe there's something of that line. But the idea now is that the phone, our receiver, can get this value. It can get, this is what we actually measure. It's our arrival time based on our phone, our receiver's timestamp, which could in principle have errors in it, relative to when the satellite actually sent the signal. So, to compare these two things, sort of in a problem-solving approach, this is what we want. This is what we have. Okay? Is that clear to everyone? Okay, so now how can we relate these two? Well then, let me just clean up some of the stray lines down here, some of these stray lines. Okay, so what we can introduce is one other parameter, this thing called tau, which is now going to be the offset between the satellite's clock, which we assume is perfectly accurate, and our receiver's clock, which we assume is off by a little bit. Serendipitously, our receiver could be accurate, but we're not willing to chance that. Okay? And so what we can do is a little bit of algebra here, and we can convince ourselves that this little ti, remember that's what we want, is equal to the big T minus tau. Okay? I mean, just take a look, plug in these things where it's this arrival time by the satellite's clock minus departure time by the satellite's clock with the definition of ti and tau, and convince yourself that that's what we're after. Okay, that works. And so what we've now developed is a relationship between this value little t, which is what we want, and this value big T, which is what we have. The one problem, though, is do we necessarily know the value tau? No. If we knew that offset, would we have to go through all of this detail? Nope. So, let me clear all of these notes off to make this readable. And so what ends up happening is that our equation that we started with, so notice here we've got our little t. This is the actual equation. That's the actual time, becomes something that looks like this form, where now we've replaced that time that we actually want with the time we actually measure and that offset tau. Okay, simple substitution. And if we square both sides, we end up getting this equation. And so now what we end up seeing, does that t minus tau term look that different from our x minus xi term? or our y minus yi? Does it really appear fundamentally different? Not really. So what this has ended up doing, in this sense, is saying that each satellite still provides us with 4 pieces of information in the 3-dimensional world. We get its x location, its y location, its z location, and this transit time, although it's now this offset transit time, at the expense that now we have how many unknown variables? Well, we already had how many unknown variables before? 3. We had our location. Where are we? And that was x, y, and z. Do we have any other unknown variables in this case? 4. Yeah, we've got tau. So we had to add one more unknown variable for our setting, which is tau. What's the offset between our clock and the satellite's clocks that have these wonderful atomic clocks that are really, really accurate? And so what ends up happening is that this ends up basically being a 4-dimensional problem, where we have now x, y, z, and tau, because we have 4 unknown variables. So think about that table that we had a little while ago. Let me actually back up to it. Erase all this off. Where we had this. And so what we see is in 1 dimension, we needed 2 signals, or that is to say, 2 sets of 2 points to determine our location. In 2D, we needed 3 circles to get our location. In 3D, we needed 4 spheres. So if we have truly a 4-dimensional problem, how many do you think we're going to need? We're going to need 5. And so you now look at the picture. 1 sphere is certainly and always the surface of the Earth. We're going to assume that we're not floating somewhere up in space or down somewhere in the inner crust. Okay? And so then if that's one of them, how many does that leave? It leaves 4. Because we needed a total of 5. If 1 is the surface of the Earth, then we have to get the other 4 from the satellites. And so that's why they actually picture 4 satellites on the Earth, because of this timing offset issue. And this is a way that we can account for that. Yep? So it depends on the homework. Most of the homework, I'm not going to make you go in, at least not in a quantitative sense, into the timing. It just gets tedious. In physics, so you can think about this as sort of being a 4-dimensional sense. Yep. Okay, so take a look over this and certainly bring questions on Monday. We'll recap this. But then just to sort of giving you a hint of where we're headed next time, is that everything we've discussed so far when we're talking about our location, it's in terms of x, y, and z coordinates. Is that how we discuss location when we talk about being on the surface of the Earth? No. We use things called latitude and longitude. And we're going to talk next time about how we go back and forth between these x, y, and z locations, which are easy to work with the distance formula, and how we actually get latitude and longitude out of that. So thank you for your attention. Have a wonderful weekend, and I will see you on Monday.